Hello everyone, this is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering. And today's topic, what we have is like FTCS, FTBS, CTCS for nonlinear equation. Okay, basically we will see how can we use this forward in time, central in space, and forward in time, backward in space, central in time, central in space schemes for nonlinear equation, and basically which one will be more stable, and we have different types of flow phenomena in general process. Let's say subsonic flow, supersonic flow, and hypersonic flow, so transonic flow. So basically we have different types of flow. So let's say if you want to use this FTCS scheme for subsonic flow, or let's say CTCS you know to use for supersonic flow. So how can we ensure that these schemes are stable, or basically which out of these three, let's say which one can be used for particular sort of problem. So we have to see. So but basically let's see first how can we write it for a non-linear equation. So here we have, so basically let's write a Burger's equation. So basically du by dt plus c into dou u by dou x is equal to 0. Okay, so basically this is actually a 1D unsteady, so nonlinear advection equation. So basically here you have this dou u by dou t, which is time derivative term, and dou u by dou x, which is space derivative term, which will be equal to 0. So now this c, so basically will be actually the velocity of the signal or any wave. So whatever we speak, so basically this c will be the velocity of that wave, okay, or the signal process, or be depend on the type of application that we have. Now if you take, let's say c is equal to u, so then what happens? So basically dou u by dou t plus u into dou u by dou x is equal to 0. Okay, so basically we have this equation, so which is of non-linear equation. Now what we will do, basically we will apply this FTCS, FTBS, and CTCS schemes for this non-linear equation. So then we will see um, 1D. So basically this is 1D equation. So now du by dt plus u into dou u by dou x minus alpha square into rho square u by dou x square is equal to 0. So basically if you take this equation, is basically a diffusion equation. So combination of diffusion, convection, okay, and unsteady terms in this equation. So how can we apply, like how do we apply this FTCS, FTBS, and CTCS schemes for this numerical equations, we will see in today's lecture. Okay, so initially let's see for the unsteady diffusion, sorry, convection equation. So now if we go for FTCS, so basically the FT is nothing but forward in time. So basically this FT, so basically this FT is nothing but forward in time. This forward in time parameter, what we have is like dou u by dou t. So this dou u by dou t will be equal to what we have. So the terms which we use to make, to write a discretized equation is superscript terms. So basically u power n plus 1 minus u power n divided by delta t. So this is forward in time terminology. So if it is 1D, so you will take only index I. Okay, so to revise, let us take again index notation. So basically if it is x-axis, let us say you have I terminology. So y it is j, and z it is k. Okay, x y z, so which is nothing but ijk. Fine. So I is nothing but along the x direction. So j is nothing but along y direction. So z is nothing but along k is nothing but along z direction. Now, since in this equation we have only x derivative terms, so what we will do? So basically we will write only the I index. So there is no need of using j and k index here. Okay, so forward in time parameter, so we are writing it as u of I to the power of n plus 1 minus u of I to the power of n divided by delta t. So this is what we have. Next term, this dou u by dou x. So this dou u by dou x term, so what we have, so basically we will write it as u of I plus 1 minus u of I divided by delta x. Okay, so this is this is actually FTFS. Okay, so basically you have FTFS scheme also here. So this is forward in time. So u of I plus 1 minus u of I divided by delta x. Okay, first actually it should be FTFS, then we go for FTCS, FTBS, CTCS. So basically we have actually four things. Now this FTFS combined equation will be, so u of I to the power of n plus 1 minus u of I to the power of n divided by delta x plus u of I into, so u of I plus 1 minus u of I divided by delta x is equal to 0. So this is what we have. So this is the equation. Okay, so now basically you should also have the time terms here, since it is explicit scheme. So if we are writing for explicit scheme, so what we have, so for the explicit scheme we have only one unknown parameter, so remaining all are known parameters. So u of I to the power of n plus 1 is an unknown parameter, so u of I to the power of n, so these are the known parameters actually. So let us write actually final form of forward in time, forward in space. Okay, forward in time, forward in space. So let us write here the full form of equation here. So what we write? So u of I to the power of n plus 1 minus u of I to the power of n divided by delta t plus u of I to the power of n into u of I to the power of, I plus 1 to the power of n minus u of I to the power of n divided by delta x is equal to 0. Okay, so this is the full form of equation. Okay, full-fledged, basically is a full equation of FTFS, which is forward in time, forward in space. So now what we do is like we will separate the known and unknown parameters. So what we do, so basically u of I to the power of n plus 1 will be equal to u of I to the power of n plus u of I to the power of n into delta t divided by delta x into u of I to the power of u of I plus 1 to the power of n minus u of I to the power of n. So this is the equation. So basically this equation so is at a particular grid point at a particular time level. So basically let's say you have I is nothing but So I is nothing but the grid values. Let's say 1, I, I plus 1, I plus 2, I plus 3, so on. So basically it will vary in this way. So this I will vary from 1, 2, 3, 4, 5, 6, 7. So basically I is equal to 1 is nothing but, let's say, first grid point. I is equal to 2, second grid point, third grid point. So this equation what we have written is solved at each and every grid point, and we will get the values of next time level. So these values you can see, these are the initial time level. So n is nothing but so n is initial time level. So n is nothing but initial time level. Then after, n plus 1 is nothing but the next time level. Okay, so we have to calculate these values for different time levels. Okay, so now let us see FTCS, forward in time, central in space. Okay, forward in time, central in space. So for forward in time, central in space, so what we have, u of I to the power of n plus 1 minus u of I to the power of n divided by delta t minus plus u of I to the power of n into u of I plus 1 to the power of n minus u of I minus 1 to the power of n divided by delta x is equal to 0. Okay, so basically here you can see the subscript term. We have I plus 1 and I minus 1. So I minus 1 is nothing but the uh, previous one. So I plus 1 is nothing but the forward one. So let's say you have the grid point here. Let's say it is I. So this point will be I plus 1 and this point will be I minus 1. So these two things. Okay, so here you have I plus 1 and I minus 1. So if you want to calculate the values at I, so for the central in space scheme, so we are using the previous level and the uh, forward level to get the value at I level. Okay, so this is what we have. Now what will be the equation? So here the same equation, but what we have here, you have I plus 1 and here you have I minus 1. So this is for forward in time, central in space. Now the same equation for backward in space. For backward in space, so what we do, basically I and I minus 1 actually. So if we take here, so this I minus 1, I plus 1. Okay, so I and I plus 1, basically this is for FTFS, let's say. So between I minus 1 and I, this will be FTCS. And now between I and I minus 1, so this will be FTBS. Okay, so here you have FTCS, which is between I minus 1 and I plus 1, which is FTCS is nothing but I minus 1 and I plus 1, which is about I. Okay, and next you have I and I minus 1, which is nothing but backward in space. I and I plus 1, which is forward in space. Now previously what we had seen is like the I and I plus 1, I and I minus 1 term for the central in space. Now for the backward in space, we are using I and I minus 1. Okay, so FT. So basically here the terms are like FTFS, FTCS, FTBS. So basically FT is nothing but forward in time, FS forward in space, CS central in space, FTBS backward in space. Okay, so the first term will be same, but here in the second term, so the u of basically dou u by dou x term is changing actually. Okay, so now let us go for CTCS, central in time, central in space. So basically we are using now central in time, central in space scheme. So for the central in time, central in space scheme, what we have, so basically u of I to the power of n plus 1 minus u of I to the power of n minus 1 divided by delta t. So previously actually for the central in space, we should use stencil size of 2 delta x. We have used delta x, but it is 2 delta x actually. Okay, plus u of I to the power of n into u of I plus 1 to the power of n minus u of I minus 1 to the power of n divided by 2 delta x equal to 0. So now this is central in time, central in space scheme. So basically central in time in the sense, so you have n plus 1 and n minus 1. Central in space in the sense, you have I plus 1 and I minus 1. Okay, so this numerical scheme, so apart like if we compare the others and this one, so what we have, the additional one is like you have time is central, but here if you take n is equal to 0, so basically that will not be applicable for this scheme. So you cannot take n is equal to 0 seconds actually. So why? Because n is equal to 0 seconds, this will be u of I minus 1. So the time is not negative. So therefore what we do is like, so this equation is implemented when after the initial one sort of simulation. Let's say initially we'll run with some sort of simulation, then we'll switch at n is equal to 1 second, we'll switch to this one. Okay, so this is what we have for the CTCS. Fine. So next, so till now what we have used is for 1D non-linear. So basically it's a non-linear equation. So if you combine, so if we combine this 1D, like let's say the advection equation with the diffusion equation, so how can we write the FTCS scheme? We'll see. 2T plus U into so this is our combined diffusion and convection or the advection equation. So if you take a Navier-Stokes equation or the momentum equation, so we have the unsteady term, we have the diffusion term, and we have the pressure gradient term, and we have the body force term. So if we like, let's say if we write the generalized equation. So here you can see the left hand side. So this first term is called unsteady term. So here these terms are called the non-linear terms. Actually, these are called advection terms, convection terms, or basically these are non-linear terms. And now, so here you have uh, minus dou p by dou x, which is pressure gradient term. So basically the motion of the fluid so will happen because of pressure gradient. So the fluid flow will happen from one place to other place because of pressure difference between 0.1 to 2. So if you have high pressure at one region and low pressure at other region, so the flow will go from high pressure to, so basically lower pressure region. Okay, so this pressure difference schemes are very helpful to propagate flow from one point to other point. When this flow is moving from one point to other point, the convection and combined convection diffusion phenomena effect is observed using this equation because of pressure gradient. So this pressure gradient is responsible for the convection and diffusion action. So if you don't have the pressure gradient, the motion of the fluid is actually it's impossible. So until and unless we have the pressure gradient, so the fluid cannot move from one point to other point. So now for the assumptions purpose, so what we have taken, so basically it is 1D. So for the 1D, what happens? So this term will be 0, and we omitted the pressure gradient term, and we have taken, and we will neglect this one also. So when we take these things, so we'll get the reduced equation actually here. Okay, so this alpha basically you can take this the diffusion parameter. Okay, so now let us write the discretized equation for this combined diffusion and convection equation. So what we will have is like u of I to the power of n plus 1 minus u of I to the power of n divided by delta t. So plus u of I to the power of n into u of I plus 1 to the power of n minus u of I to the power of n divided by delta x minus alpha square, which is of u of I plus 1 to the power of n minus 2 u of I to the power of n plus u of I minus 1 to the power of n divided by delta x square is equal to 0. Okay, so basically here you can see the when we compare, so the equations, so when you see FTFS, you have I plus 1 and I terms. Okay, so only two. So when you see FTBS, you have I and I minus 1 terms. When you take FTCS, okay, so you have I terms, I plus 1 terms, and I minus 1 terms in the current equation which you are discussing. Okay, now when we take this equation, so which is combined convection and diffusion equation, so the number of variables which are present here, you can see is here 1, number of parameters 2, 3, and 4. Okay, so and here if you take a normal 1D equation, only the convection term, so here you can take 1, 2, 3, and 4. Okay, so basically these parameters, whatever we have for the uh, for the for the FTCS, and here the combined diffusion equation, so are the same actually. So here what I'm trying to say is that, so whatever the equation we have, whatever the scheme we use, so the number of parameters involved to get that particular value at the next time level is very important. Okay, so why? Because if you are relying on the low or the less number of parameters, so then in order to acquire the next value, or in order to acquire the value of velocity or temperature pressure at the next time level uh, will be inaccurate actually. Okay, so here you can see the equation is somewhat like you see lengthy, but this combined diffusion convection equation so is written in general form. Now this u of I into n is getting multiplied with this one. So this non-linearity thing we have to take it out. Okay, so we need to linearize it and write it actually. Fine. So basically I have just written, so whatever the equation or the expression that we have in the general form. Now basic thing what we need to do is like, so the nonlinear equations we have to linearize it, and we have to apply the appropriate scheme. Then in the next session what we see is like, so whatever the discretized equation we have, so we have to see its stability and we have to see its convergence. Okay, so stability of a numerical scheme will majorly depend upon the oscillation of errors actually. So with respect to time, the oscillation of errors are getting reduced, or let's say the error is decreasing with respect to time, then you can say it is stable. So if the error is increasing with respect to time, then you say unstable actually. So you will do some factor or you will do some things to damp the oscillations, or stability criteria has to be seen. So what sort of conditions, what sort of constraints has to be used to ensure that a corresponding numerical scheme is stable and it is getting converged for a particular problem. Okay, so in the next class we'll be seeing, so stability of a scheme, convergence of a scheme, which is very important actually. So when can a numerical scheme can be stable? So explicit scheme is there, implicit scheme is there. If you take explicit scheme, is it conditionally stable or is it unconditionally stable? Implicit scheme is also there. So whatever the things we have done is for explicit schemes. So we can actually do the same purpose, same equations, same way in implicit also. So which sort of scheme is stable for which type of problem, and how to choose this particular numerical scheme to solve those things, we have to see it actually. So without stability of a numerical scheme, it's very hard for us to model the fluid flow simulations actually. So stability, convergence are the very two important parameters. So basically consistency, so basically consistency is, so stability convergence has to be met to have be to basically to be consistent, but the convergence and stability are very important factors for the simulation. So when we are using a second order numerical scheme, so how it can be stable? So if you are using explicit scheme or if you are using implicit scheme, which sort of thing is stable we need to see. And then after, first thing is we have to see whether it is getting converged or not. And for let's say shock flow problems, let's say for subsonic flow problems, let's say you have hypersonic flow problem, so which kind of numerical aspects we can use, or let's say you have other aspects. Okay, so not about the shock flows, hypersonic or these things. So let's forget about, let's say it is incompressible flow. So for the incompressible flow, the flow propagation, so which type of numerical scheme can be used, so these things has to be seen. Okay, so but before that we need to evaluate the scheme whether it is stable or not, whether it is convergent or not. Okay, so for the next class we will be seeing the stability of the numerical scheme and the convergence. Okay, thank you.
Like, share, and subscribe. Hit the bell icon for more updates.